Welcome! In this lesson, we will build a strong visual understanding of reverse and thrust fault systems and the landforms they leave at Earth's surface. We will see how low-angle faults in compressional belts push crust upward, fold surfaces, and imprint subtle but diagnostic geomorphic clues like uplifted terraces, linear mountain fronts, triangular facets, and stream anomalies. First, an intuitive cross-section. Imagine a gently dipping fault plane slanting down to the right. The block above the fault is the hanging wall, and the block below is the footwall. In a thrust fault, the hanging wall moves up and over the footwall, shortening the crust. Compression pushes from both sides. As slip accumulates, a low, broad mountain ridge forms, and near the range front, a fault scarp or flexural scarp can appear in soft sediments. What do thrust faults leave on the landscape? For key surface clues stand out. 1. Range front fault scarps or sharp flexural scarps in young sediments. 2. Uplifted and tilted river terraces or alluvial fans on the hanging wall. 3. Stream anomalies, nick points, steep short reaches, diverted channels, and ponding for triangular facets and straight mountain fronts where uplift outpaces erosion. A classic example is the Himalayan thrust belt. The frontal emergent segment of the master fault, called the main frontal thrust, also known as the Himalayan frontal thrust, marks a sharp boundary between the mountains and the Indo-Gangetic plain. Along this front, discontinuous scarps, a few meters to tens of meters high, cut young alluvial surfaces. Flights of river terraces are uplifted and tilted, with uplift rates of roughly 4 to 10 millimeters per year at the outer edge. The mountain front often shows a sawtooth or scalloped outline where big rivers carve water gaps through the uplifting ridge. How do we quantify activity at a thrust front? Two handy metrics help. Mountain front sinuosity, spoken as SMF equals LMF divided by LS. Low values mean a straighter, youthful front. Stream gradient index, spoken as SL equals local slope times reach length. High values at folds or scarps signal active uplift. Let's compare a straight, youthful front and a dissected, older front, and place a river with a nick point on each. Not every thrust breaks the surface. Some ruptures are blind, bending the ground upward to form a flexural scarp, a gentle step without a clean break. Others bring the fault tip to the surface, creating a discrete rupture scarp with a sharp break in slope. Both record the same story of shortening and uplift. Some thrusts carry a sideways or strike-slip component. In these oblique thrusts, ridges can shift sideways across valleys, forming shutter ridges and pond zones. Let's put this together into a quick checklist. Look for 1. Range front scarps or sharp flexural steps in young deposits. 2. Uplifted and tilted terraces or fans on the hanging wall. 3. Linear or sawtooth mountain fronts, sometimes with triangular facets. For stream anomalies like nick points, ponding, and diversions. 5. In oblique zones, shutter ridges, and small closed basins. These clues together signal active reverse or thrust faulting and ongoing crustal shortening. Excellent work. With practice, you will spot these patterns quickly in maps, satellite images, and topographic profiles.